My name is Eng Lim. I'm now a HPE employee, right? Since HPE acquired SGI. I'm the Vice President and SGI CTO at Hewlett Packard Enterprises. My job stays the same. I go out and meet industrial partners, look at their visions, their passion, their desires as to the roadmap they would like to take in HPC. I do about 100 briefings a year and co-design sessions. But more recently, I've been seeing a change. And I thought I come up and talk about this change to this group. The one that motivated me, got me started thinking about this change and how I relate to the customers that I'm hearing with regards to their new vision is this from NSCI. It's not just exaflop of compute power, but also the ability to analyze exabyte of data. So that was the key. So there's the HPC, and I'll just simply say there is also the HPA side of things. Let's have a look at those customers, right? Those industrial partners. They take two paths ultimately to discovery. The goal is discovery. I mean, you can start with a hunch, hypothesis, theory, experiment, and so on. But the goal is discovery. For the HPC world, they tend to start with a hypothesis, go through theory, run their experiments, build their models, and hopefully they discover, right? For the HPA world, a lot of them are in the data analytics, fraud detection, the fintech world, the financial analyst type world. Maybe they start with a hunch. Yeah, I used to spell wrongly a hunch with an A, right? So it's hunch, hypothesis, and ultimately discovery. But it could be a mix, right? The key point here is they borrow from each other, although not recognizing the other's contribution as much. I think the world has to change. There is also a new desire to make serendipity an intention. I'll talk about that a bit more also. Yeah. And there was a question whether the two paths are converging. They are. You know, if you go to Wall Street, they used to say those financial modelers used to be rocket scientists. You know, they hire rocket scientists, essentially physicists, right, to build financial models. So there is starting to be a cross-pollination between the two, right? Once they hire them over, the physicists, they got them to run analytics. Yeah. So let's have a look at HPC and HPA, just as a simplification, right? In the HPC world, we build our models with fundamental principles, you know, conservation of energy, mass, and momentum, right? Hopefully, we have those equations for us. But there are times where we don't have those fundamental principle type equations. We rely on maybe more empirical information, right, to create our equations. But ultimately, you send in your initial conditions, and then you get lots of data out. So you do an input, your function, and your solution, and you don't quite know what the solution is, but at least you have your fundamental principles in the form of equations and a function. You send your inputs in, and you get lots of outputs, right? That's essentially a very simplified way of describing it. The way I do it this way is so that I can show you what's on the right. We call that simulation. So what's on the right is HPA. And it's common that you take in lots of data, and then you produce an insight. It could actually be a single bit. This drug is good or no good, right? Yeah. And here, typically, a typical operation here would be search. You take a huge haystack in, and then you get your needle out. Right? So essentially what happens in the middle is search. And you hire analysts, data analysts, data scientists on this side, and you hire HPC application specialists, right, on the other side. You hire your analysts on this side, and their job gets tougher and tougher each day because the data volumes are growing. And there are other problems. And that's the reason why I believe, other than the traditional analytics on the right, you're starting to see an emergence of machine learning. And these are the 4 reasons. from what I've heard. Why on the HPA side, people are leaning more and more towards machine learning. First and foremost, humans operate by filtering data rather than accumulating data. I'm not saying one is better than the other. I mean, we live in a very noisy world, so we are just specialized in filtering things out that we are not interested in. Like in a noisy room, we can still have a conversation. We filter it out. But sometimes that's not a good thing, right? But a machine does the opposite. It accumulates. Also, sometimes that's not a good thing, right? But one should not be done in isolation of the other. Moreover, we grow up with a bias. Now, as professionals, we work very hard to suppress our bias, but it's there. Yeah. So these are the things with regards to a human being the only entity in the analytical loop. Secondly, big data, right? Big data has now overloaded our analysts. So now it is time to automate or give more automation to our analysts. This is what I've heard also. Our analysts, we just can't hire enough analysts. The data is so huge that they're overloaded. We need to automate or create automation for them. Right? The other thing I've heard is now data is accessible. There used to be big data everywhere, but now it's easier to get at that data. Internet, for example. Download the fire hose from Twitter, right? Pay a bit and you get all of it. Yeah. And low cost. It got so cheap enough, maybe in the future, you don't need to apply and do HPC type computation to get at your answer. Maybe you can just keep guessing until you get the answer. If it's so cheap, right? Can you just keep guessing until you get at the answer? That was the fundamental thought, right? Let's just say I now have a number in my head between 1 and 1 trillion. But I give you 1 trillion chances to guess that number. Naively, eventually you get the answer. Now, I'm not saying machine learning is that, but essentially that was the motivation, I believe. Right? If I have enough compute power to waste at this problem, will I eventually get the answer anyway? Can I keep training until I get a good way to get at future good answers? It got cheap enough. Moreover, you don't have to guess very precisely. Right? All I need to tell you when you guess the next number in the trillion is that, oh, you are too big or you're too small. And ultimately, you will converge, right? Yeah, maybe in less than 1 trillion steps. So these were the motivations for them to look at machine learning as a way to solve the problem on the right, with not just traditional analytics. Yeah. And so what has been emerging, right? You have your input, your function, and your solution. The thing here is that you really know the solution. You assume you know the solution because there's so much data with the right answers. You have so much data of climate models that people believe is right. You have so much data about drug discovery that people believe is right. Can you but what you don't know is the equation for the discovery. What is the equation for identifying cats in pictures? There is no equation, right? There's no first principle conservation of energy, mass, and momentum to get you there, right? There's not even an emergent property that climate modelers use, right? Where I say, I don't have an equation to understand El Nino because it is an emergent property of a complex model. So in fact, people on the right here don't really have all the answers either. Yeah? Anyway, since you don't know the function and you know the solution, can you then not just put an adder to it? Just add. And then take all your inputs and put importance levels called weights, yeah, in front of all these inputs that you're getting from the left. And then you infer your solution. If you get it wrong, since you know the answer, you get it wrong, you keep working on it until you ultimately reduce your errors to to start predicting right answers. So that's essentially what machine learning is, deep learning machine learning is. So you can see the two worlds are highly complementary, right? There are those that are now starting to think maybe I take the outputs of all the years of simulation I've done that is in some backup somewhere, take them all back out to train my models. And ultimately, I can predict where the fault line is and where the oil will be, instead of running seismic simulation to discover where the oil is, right? Can I then not just infer where the oil is? Yeah. So all this is what I've learned. And I think ultimately, this is what I believe will become our future. Right? theory in hundreds of years ago was backed up by experiments. So we actually dropped the ball from the Leaning Tower of Pisa and this figured out gravity. We ran the experiment. Then over the last tens of years, simulation came to become strong enough to stand on its own. There are cases where you cannot run the experiment, but you need simulation to prove that your theory is right. By the way, as a side note, simulation has still not got high enough for the Nobel Prize committee, right? Yeah? You still won't get a Nobel Prize unless you prove your theory right with experiment. Yeah? Right? Yeah, that's the reason why Stephen Hawking's black hole theory doesn't get Nobel Prize until we create one, right? So that's, a small one, yes. I believe inference will eventually come up to be that, inference will eventually come up to be the third part of things, yeah? You infer an answer, right? I mean, we have wild guesses, we have educated guesses, and then maybe we have inference. I don't know, right? I mean, the whole world is still coming to terms with all these ways of getting at discovery. Right? Yeah, I believe it will become the third leg to theory. Yeah. But the key thing to get there is taking too long to learn. I mean, we're talking days, weeks, months, right? In unsupervised learning, one experiment ran for 3 months on a huge data center servers, right? Just to learn how to do something. But the neat thing is we can scale machines. We can't scale humans, right? Well, it'd be great if a grade 1 kid goes the first day to school in the morning, and the afternoon he or she comes back with a college degree, right? You scale, right? But you can't scale that. But you can scale machines. So we've seen people trying, right? The DXG Saturn V, right, is number 28 in the top 500. It's designed just to learn fast, right? It put about 1,000 of those NVIDIA P100s in a very dense form factor. And most importantly, it has all the connections required to feed this machine fast enough. Because if you learn in a scalable way, you'll be very hungry for data. You're doing very simple computation, but consuming massive amounts. So your problem is bandwidth, how to feed this machine fast enough. So we were asked to build a machine even bigger, and we did it. Yeah, it's 2,000 of these highly networked P100s, right, in a scalable way. And we are installing this system right now in Japan. Right. This is just a data consumer. Let's just have a look at one of those nodes in that system, a data consumer. There are 4 P100s. The 2, eventually will be Skylakes, right? This could be Voltas. You will notice that firstly, not only are the CPUs connected through 4 Omni paths going out, the NVIDIAs are connected by NVLinks, high bandwidth, and they also have GPU direct. So clumps of 4 P100s that is doing learning can talk directly to other clumps of P100s doing learning. So you can see for scalable learning in a general way, I mean, some specific learning is highly embarrassingly parallel, but others are not. You need to be able to feed in a very high bandwidth way. And then the last thing about this is about this third leg, other than in order to learn fast, we need to scale well. So that will be where, for example, HPE will be investing in AI system, how to scale learning. The second thing is how to take note about inference is this issue of not being able to validate your results. I was told by some drug discoverers that inference is starting to be thought of a way to discover drug candidates for biological targets. Because this screening is just too intensive. It takes 10 years to certify a drug, right? Discover and certify a drug. Can use an inference method to discover drug candidates for biological targets. But they said if it was inferred, even if it was a useful drug, they may not pass FDA, right? Because they cannot explain why. Why? Oh, the machine told me, right? So why, this one really got me thinking, right? Because this next few slides will tell you the story behind not being able to tell why. In 1997, Deep Blue beat the world top poker player. Few people know that actually in 1995, Machine beat the top checkers player. And then 2016, just last year, AlphaGo beat the top human player in the most complex game called Go. You can see, in terms of naive complexity, how much bigger this game is in combinations. Yeah. You know, after AlphaGo beat Lee Sedol, the developer for AlphaGo was asked this question. You know, during that final game, the interviewer asked the developer of AlphaGo, during that final game when AlphaGo did this particular move, do you know why it did this move that actually won the whole match? You know what the developer said? He stared at the interviewer and said, I don't know. He developed AlphaGo, right? And he just said, I don't know. Why? Because he developed the supervised training to train AlphaGo, but it also did reinforcement learning, which means he supervised trained two entities of AlphaGo, and once he got to a certain stage, he let two of them go play. It's just like putting training two kids after grade 1. In grade 2, you let them out to learn from each other. And then the teacher steps further and further back behind, right? Then ultimately, you don't quite know. After 10 years, right, the two kids come back, learn from each other, right, are quite different from what you thought them at the beginning. And this is what's occurring, right? And we saw it one more time. This year, the HPE system with the CMU Liberatus poker software, now this is going to be a very valuable piece of software, anyway, right, beat the world top 4 poker players. The year before, this same piece of software, the generation behind it, lost $700,000. This year, it won $1.7 million. Last year, it was criticized for losing because it didn't bluff well enough. This year, guess what? When asked the 2 questions of the 4 top poker players, what was the most amazing thing about Liberatus winning now? It bluffed really well. You see, it learned fast in 1 year. Huh? Yeah, so it really got me thinking, right? Of course, we needed to build a machine that's 10 times faster than the previous one in order to gobble up all that data to learn that fast. Yeah, it took a year, maybe less, right? But it became the best thing about the machine learned program as opposed to the worst thing about it. Yeah. The second thing, it was us, the developer of the CMU Liberatus. Why did it bluff better? Same answer, I don't know. Reinforcement learning. See, the powerful thing about reinforcement learning, when you put 2 machine entities to learn from each other. So anyway, the point here is, I don't know, you hear a lot. I got a good answer, but I don't know how I got it, right? You have to get used to that, and maybe us in the industry will have to get used to that, right? I don't know if it's acceptable. In the same way, between experiment, inference, and simulation, the Nobel Prize community has not even accepted simulation, let alone inference, right? So I think we'll have to see. Right? So I hope from this you get some ideas, right? Now, if the machine can, people ask me, is Liberatus ready to start reading people's faces and assess the bluff factor of the opponents? This will be the next thing, right? But it on its own is already beating the top poker players. Actually, this was the machine was sent to China, and it beat the 2 top poker players there too. Only a few weeks ago, it was in the news. So they called CMU over and tested it, and it won again. So it's going to be hard to beat this one. It's Texas heads up, no limit. Right? That's a particular kind of poker. And then finally, actually I planned only for 15 minutes. That was in your agenda, actually. But never mind. If there was a question, we'll answer them. And finally, the third thing about it is how you feel about it. Right? First, we have to understand that inference is something that sometimes we can't explain the results. But thirdly, as a machine learns so fast and scale, what will they become? I'd like you all to watch this video. I only took a very short part of it, short clip of it, so that it won't be controversial. Yeah, okay. Yeah, I'm going to work hard, work hard. Oh, stumbled. Never mind, never mind. I keep going, right? Yeah, work to do. Let's pick it up and keep going. Oh, you're being funny with me. It's okay, it's okay. I come back. You know, raise your hands if any one of you just felt a bit bad for the robot. Yeah, there we go. I didn't show you the second part of it, right? You know, the guy was like, you know, really harsh to the robot, right? Now, if this is 2015, right? Imagine 10 years from now how you will feel for that robot, yeah, with the AI software in it. So I conclude by the following, right? Just to bring everything together, yeah. There is HPC simulation. There's converging with people that are getting too inundated with data. Analysts that are getting too inundated with the data. They are thinking up ways now to automate their work. And that's what machine learning is. And that's the relationship. A machine learns to be artificially intelligent. But there are other ways to become artificially intelligent. Expert systems, rules-based, right? That was what the chess program was. It was based all on rules, right? But the machine learning approach is different. I'm just going to guess until I get it right, because guessing is cheap. I'm simplifying it, right? True AI expert will scold me, but for this audience, I'm just going to say it, right? And then, okay, there are expert systems, right, that could get you to be artificially intelligent. So I'm not saying that one is at the absence of the other. You'll start to see AI systems that are a combination of rules-based, which is the expert system, and guessing-based, which is the machine learning. Okay? Guess until I'm good, yeah. Yeah, the question is, if you send a kid without any training, unsupervised, right, into a library, and then 20 years later, what would it be, right? It could be interesting. And then if you can say it can come out intelligent, then if you use a machine, then you don't have to wait 20 years, right? So these are the types of concepts they are thinking. Right? Okay, and a method of machine learning is neural network. And this is where you try to simulate the brain, and then you just feed it data. And hopefully, ultimately, it learns. Yeah? And that's only a single-stage neural network, right? And there are other ways to learn. You can classify, you can cluster. There's so many other ways. Machine learning is not the only way to learn, to become intelligent. There's so many other ways, right? And they are classified by either supervised learning, where there's a teacher and a pupil, unsupervised learning, where you just say, go to the library and don't come out until you're intelligent, right? And then reinforcement learning, where you put the two to work on each other. Classification is a supervised learning method, and clustering is an unsupervised learning method here. And then finally, a multi-stage neural network is called deep learning. And that's essentially what I've learned. It's not so much what I've learned from textbook. It's more what I've learned from talking to these people out there, right? From the financial industry to industry that are building products, where they are directing their energies now, right? Can they infer discoveries, right? That's an interesting one, right? Perhaps it's even going to be better at serendipity than the traditional method. So you see, they're starting to think all that. All this is in that YouTube video that Rich recorded as an interview. So they're all in that 14-minute interview, if you would like to get back at those material. Thanks, Rich, for doing that. On that note, thank you. Yeah. Quick. Yeah.
I'll ask you.
Yeah.
So I think this issue of not being able to understand why an AI system might make a certain decision or go a certain way is very important for certain classes of problems, right? And a lot of it has to do with the fact that there are certain decisions that we want to be made by a human, right? Because it's rich, complex. But at the end of the day, the human brain is using these same algorithms to learn as the machines are, right? So there's a comfort level and sort of an understanding of why things happen, but there's a concern about when you try to retroactively explain decisions like that in complex situations, they tend to almost always be simplified and wrong. You know, Gladwell did this book called Blink, where he looked at how people in very complex time stress situations made decisions. And you know, he was looking at how does intuition work. And so when he asked military commanders, Wall Street traders, how they made decisions in a certain situation, they would come up with an explanation of, you know, the logic they followed. But they found out very quickly that that explanation was oversimplified and wasn't, in fact, how he made that decision. There was a recent article I saw in one of the Google research threads that looked at when they took Google Translate over to a machine learning type of approach, and it appeared that the system created sort of a universal language that it translated everything into and then translated everything out of. And there's a sort of a question of, well, did it really do that? Did it just appear to do that because, you know, that's what the researchers looked and saw the patterns forming and that kind of thing? I wonder if you could talk about whether there's a need for us to investigate more how one derives explanations for how these things happen to maybe facilitate us coming up with good and accurate explanations for why these things happen.
This is a great question. In fact, it's even pushing to the point of philosophy, right? Let's put it this way. Even in simulation, we think we know all the equations really well. Yeah, the conservation mass energy, momentum, clearly, fundamental principle. But when it comes to things like Navier-Stokes equation, right, our understanding starts to take a step back, right, a little bit. And then now you talk about scientists talking about emergent property in complex systems. You know, they can't formulate an equation to describe why a dust devil touches down in this way and moves that way. But they say it is the result of an emergent complex system, right? Yeah. So even here, we don't quite know. This is even further out. Right? So one way, to describe it, I think we are far away, right? To describe how we come up with decisions the way you're asking. Even here, we are not there, let alone there. So the solution for many of them is that, for example, in drug discovery, use inference to point you in the right direction, and then to use the traditional method to validate that the drug is correct. And the pharmaceutical industry is not unfamiliar with it. If you heard about, they call it forward pharmacology or reverse pharmacology. We used to do forward pharmacology, meaning we extracted something, you know, and then we fed it to someone and it worked, right? Then we go and figure out why it worked. That was the traditional method. Until recently with DNA sequencing and so on, we did the reverse pharmacology method, which is very precise. You target a particular protein, right? So do look that one up, because that one also, we are used to that. So I believe the drug world, which is the strictest of all, I believe, of many, right, would use this as a guidance to point things, yeah. So.
Isn't part of the dilemma because where the goal with this is not teaching machines to think like humans, but teaching machines to produce results, the same kinds of results that you think you need.
That's right, and that was the point. Yeah, very good point. That's why I forgot to mention it here. You'll notice all these benchmarks were specific to being able to be better than humans in that specific area, right? It's not general intelligence, it's specific intelligence. The question is, after you've developed 1 million specific intelligence, and then you combine them, can that be an emergent property? And then that machine becomes sentient. I'm starting to be crazy now, right here, right? But you know, scientists are using the term emergent now, right? Because they can't explain it, right? So, good point. Yeah, artificial specific intelligence, and all they need to do is just prove that we can be better than humans at this particular function. And then you just put it, let the machine go at that problem that it's good at, so that it offloads the analyst. So ultimately, we become supervisors. If you look at the early industrial revolution to now, more and more become supervisors of machines, right? The human value factor. You look at the machine and made the good decision, but I'm here now as a human to decide whether value-based, we should still go ahead with it. Yeah. It may be a good or correct decision, but human value-wise, it may not be acceptable. Yeah. So I say no. So you override. Yeah. So ultimately, we still have jobs. It'll just be it'll be a supervisory role.
So let me suggest that maybe this is not a bug, maybe it's a feature. Because decades ago, I learned a definition of intelligence is powerful behavior which we do not understand. The moment we understand it, we say, oh, it's not intelligence anymore. So if you want artificial intelligence, then you shouldn't understand it.
Yeah, and we are there now, right? Yeah. So maybe there should not be an incentive to understand it. Yeah.
But there are real philosophical and ethical questions associated. Absolutely. If you don't understand it,
Yeah.
and you go with it, then does the AI really, is it in control?
Yeah.
Where do you want control to reside?
So that's why, at least for state of art today, they act as a guidance. They point us rather than decide for us. We ultimately decide. Yeah. Yeah. Sorry. Yeah.
So, by looking at the way that we're utilizing it now more in medical world, we're really trying to uncover evidence for a decision that the human can't do fast enough. If you look at the way a floating point unit was created, it goes a whole lot. It goes a lot faster than a human can calculate. I can't add as fast as a computer, right? I can't assimilate the information necessarily as fast, but it can go through and find the evidence that my pathologist or my MD or whoever can look through. So really what it's trying to do, what we're using it for is to try to make sure that it's more reliable in the sense of looking at all of the evidence.
Yes.
To be able to also then take out as much of the bias as possible.
Yes.
Because somebody is now tired or somebody has a different set of skills.
Yes.
And so this now is starting to inform the teams that we have that come together. So it's really
And
an
the third point
evidence type of discovery system.
Yeah, and to add to that, because we are a fundamental filterer, you don't know if, because of that mechanism, we actually filtered out that serendipitous discovery, right? So yes. That's why we are not unfamiliar with this, I keep saying. The forward pharmacology, read that one up. That has been our fundamental drug discovery process, right? And we did it that way. We just discover something that works first, and then we later find out why it works, yeah. So perhaps this will be that. Yeah, sorry.
Jay did it again, over two.
Oh, okay. Oh, okay. We're okay? Yeah, thank you. Yeah.